Hey everybody, Mr. Smith here. In this video lesson, we are reviewing some work and energy concepts from the grade 11 course. So if you are feeling pretty confident in those skills, you do not necessarily need to work your way through this whole lesson or do the associated practice. But if you want to brush up or feel that you need that, then maybe you should. So let's get started. So what is work? Well, work, and we use the symbol W for work, it's the energy transferred to an object when a force acting on the object moves it through a distance. So since work is energy transferred, the units of work are joules. And the formula for work was most likely something comparable to this from your grade 11 course. Work equals force times distance times cos theta. So the formula here, for those of you who have taken calculus, may have hopefully this was familiar. It's usually kind of a standard part of the calculus and vectors part of the course. That's the dot product between force and displacement. If you haven't taken calculus yet, not a big deal. You just use this formula. And that angle theta there is the angle between the force and the displacement. And this F and this D, this delta D, they are magnitudes. So it's like the magnitude of the force and the magnitude of the displacement, so distance. So this formula is interesting because if you've taken the grade 11 course, you know that the cosine for angles that are bigger than 90 degrees, between 90 and 180 anyway, are negative. So you can actually have negative work using this formula. And that happens when the force and the displacement are in opposite directions. So for example, if I can find my cursor, if we had a force acting this way and the object moved in, say, a direction this way, well, I think we could all visualize, the force is kind of causing the object to move. It's adding energy to the system. And so we say positive work is being done. But if instead we had an object that was moving this way and with the same direction of force being applied, then I think we all could have visualized that the force would be slowing it down and removing energy from that system. And so we would get negative work done. So you can't have negative work. It kind of happens when force and displacement are in opposite directions. So in these cases, the force is removing energy from the system. So work can be positive if energy is being added to a system, negative if it's being removed, and there's three cases where no work is done. And it basically comes from the three variables in the formula work equals force delta D times cos theta. So if there's no force, there's no work. So that's pretty easy. The second case is if the displacement is zero. So a force may be applied, but no energy is being added to the system. A classic example might be pushing against a wall or something very, very, very heavy. And if the wall or what you're moving is not being like crumpled or anything or deformed, that force you're applying is not moving it. There's no work done. You're not transferring any energy to the wall you're pushing on. And finally, the third part of that formula, if I can flip back for a second, is cos theta. And if you recall from your earlier math courses, or if you want to check on your calculator, the cos theta is 0 when the angle is 90 degrees. So I might add a little something there. So when does cos theta equal 0? That implies the angle is 90 degrees. So in those situations, there's no work being done by whatever force you're talking about. If there is work being done, if energy is being added to the system, then it's not being done by the force you're talking about that's perpendicular to the displacement. Let's do a few simple examples involving work. So here we have a store employee, so raising a case from the floor to a shelf, and note they're raising it up at a constant velocity. And then later on, they lower the case 1.05 meters from the shelf to a cart, and again at constant velocity. And so we're going to ignore the fact that the case just goes from rest to moving instantaneously. We'll ignore those short periods of acceleration at the beginning and end. We're going to find the work done on the case in each of these scenarios. So by the employee as the case rises, by gravity as the case rises, and by the customer as the case descends. So just to start off quickly, just going to squeeze in, I might even squeeze it in right here, just the tiniest of tiny free body diagrams. So in all the scenarios for this lifting up and lifting down the crate, you've got its own weight pulling it down, gravity, and you have the employee holding it up with an applied force. And in each of those cases, the applied force and gravity are equal to each other. Because the acceleration is zero, because it's moving at a constant velocity. So before we begin, let's just think about which direction the motion is in each of these. So in part A, the case is rising. So we'll use up as positive, and we'll say that the displacement is up. In the second case is when the case is going up. In the third case is when the case is going. The third case is when the case is when it's going down. So let's look at part A, and let's use our formula for work. So work equals, and because we're talking about the employee, we're looking at the work the employee does on the case. So we're looking at the forces there, what the force they're applying to it, their applied force, times delta D times cos theta. And the applied force is just, as we talked about, it's just equal to mg. And we know all these things. The case is 8.72 kilograms, G 9.8, and the displacement from floor to shelf, 1.72 meters. And what do you think the angle is between the applied force and the displacement? The applied force is up, and the displacement is up. That means the angle between them is 0 degrees. So let's finish this off. 8.72 times 9.8 times 1.72. So I got about 147 joules. Now you may be wondering, well, if energy is being added to that system by the employee, what is happening with gravity? What's it doing? Well, in part B, looking at this one, we have the work done by gravity as the case rises. Well, that work done is just mg. And we'll have some different value for theta here. So what's different? Well, the mass is not different, 8.72. Remember, here we're looking at the work done by gravity, right? So Fg, but that's also just in magnitude, that's just mg. As the case rises, the delta D is, or at G is 9.8, delta D is still 1.72, but gravity, that force is acting down. And as the case moves up, that's up. What's the angle between down and up? It's 180 degrees. And what you get is, well, you get the exact same value, just negative 147 joules. So in this case, gravity is removing energy from the system. And it makes sense for those to kind of balance out, because if it's moving at a constant velocity, its speed is not changing at all. Now let's look at part C. What is the work done by the customer as the case descends. So same scenario as part A. You've got an applied force by the customer, some distance, some angle. I'm going to squeeze this in here. So the applied force is still mg. The free body diagram holds for each of these parts. Delta D in this question, though, is going down. So the size of that is just 1.05 in this formula. Actually, I'll just use delta D cos theta and put everything in the next step here. So the mass is still 8.72. Gravity, 9.8. This distance is different, 1.05 meters. Again, that's a magnitude. And now, what's the angle between the customer's applied force and the displacement? Well, here the case is lowering, and they're applying a force upwards. So the angle between them is 180 degrees in this case again. So let's calculate this. So I got negative 90 joules. So you can think about it like that case, it will actually, gravity wants to cause that case to fall to the ground. And so the customer, by lowering at a constant velocity, is actually kind of removing energy from that system. So it does make sense to get a negative value. So just a couple examples, playing around with that formula, talking about positive and negative work. Let's go on. So you would have learned in your grade 11 course the work energy theorem. So what is the work energy theorem? So it says that the total work done in an object is the change in the object's kinetic energy, provided nothing else in the system changes. So we can write that as a formula. Work is delta EK. So, so for example, if we're not, and we'll talk about gravitational potential energy in a moment, but if nothing changes, we're not lifting anything up in the air, or if we're keeping at a constant, like say level surface, if I do work on an object, I'm going to change its speed and I'm going to increase its kinetic energy. So a more general form of this equation is that work is just change in energy, period. But in grade 11, you just focused on scenarios where the work you do just causes something to speed up. I think we're going to do a couple examples just to try that out. And of course, actually getting, maybe I should on the previous slide here, actually. Quickly review kinetic energy. And again, you guys, this is the energy of motion, and you guys would have spent some time last year showing that the kinetic energy of a mass, m, moving at a speed v, is 1/2 mv squared. But you guys probably all have that one burned into your skulls at this point. Let's do a couple examples. So what total work in megajoules, so mega is the prefix for million, is required to cause a cargo plane with a certain mass to increase its speed and level flight from 105 meters per second to 185 meters per second. So the level flight is kind of indicating, okay, nothing else is changing here. All the work by burning this fuel to like accelerate the plane is pouring into increasing its speed. So our starting point is going to be work equals change in kinetic energy, which is 1/2 mv2 squared minus 1/2 mv1 squared. So if you'd like change of kinetic energy is that's just final kinetic energy minus initial kinetic energy. So I'm saying EK2 minus EK1. If you like EKF and I for like final and initial, as we talked about, you just do what you're comfortable with in whatever from your previous course. So we're ready to calculate. We can probably make our calculation a bit quicker if we just factor out 1/2 and m and just do v2 squared minus v1 squared. Maybe just a little bit less calculations. But yeah, we're basically at this point just plugging and playing. 4.55 times 10 to the 5. And then we have v2, 185 squared minus 105 squared. Let's see what we get. 2, times 185 squared minus 105 squared. All right, so just going to double check with what I got earlier. Yeah, I got the same thing. So I got 5.28 times 10. That looks like 90. Yep, that's times 10 to the 9 joules. Question wanted that in megajoules. So to get megajoules, 1 megajoule is 10 to the 6 joules, a million joules. So if you divide out a factor of 10 to the 6, you're left with 10 to the 3. So it's 5.28 times 10 to the 3 megajoules, or 5,280 megajoules. So kind of a simple problem, just playing around with the work energy theorem formula. Nothing crazy there. I believe we're going to do a second example. So we're just going to, a second example, we're going to be solving for a different thing in this case. So we're going to use the work equals the change in kinetic energy. But here we have a fire truck that's moving along and has negative work done onto it, which is implying that energy is being removed from the system and the fire truck is slowing down. And it slows down to some speed of 11 meters per second. We're going to find the initial speed. So work equals, and I'm just going to go right to 1/2 mv2 squared minus 1/2 mv1 squared. And you can just plug everything in and solve in this case. I'm going to just do I might just rearrange for V1 first and just maybe review a few math skills with you guys. So a common strategy with energy problems is you often have a lot of 1/2s floating around. So by multiplying the entire equation by 2, and I might actually at the same time factor out an m just to have less stuff going on, can be a nice way to remove fractions and just make your calculations easier. So I'll divide by m. I'm actually going to move v1 squared to the left and 2w over m. I'm going to move it to the right. And then hopefully you can see that we're going to be taking the square root. Now, I'm not going to include plus or minus here in the square root because when using the kinetic energy formula, v is just the speed. So we're not concerned about the direction here. So we get the root of v2 squared minus 2 times the work over m. So yeah, let's find this out, guys. So v2 is 11 squared minus 2 times, that's minus 2.9. And note the prefix m is for mega. So that's times 10 to the 6 joules. And the mass, 1.63 times 10 to the 4. But yeah, I mean, this is just another example of playing with the formula. Nothing crazy new here. All right, I might do that one first. So 2 times 2.9 x6 divided by 1.63 x4. We're adding that on and then square rooting. So we should get something larger. So I got 21.8 meters per second, matches what I did earlier. And that seems pretty reasonable. We've got the initial speed of the fire truck. So just playing around with the work energy theorem, a couple of review examples in the books. I just want to stress as well, like I won't be testing on this. This video is purely for review. These are kind of skills we should be coming into the course with, but I think reviewing them in my experience just helps the next several days of lessons go by a bit smoother. Great. Let's talk about gravitational potential energy. So this is energy stored due to a change in elevation above the Earth's surface. So I am going to write a little formula for that. So depending on who taught you, you may have different ways of writing gravitational potential energy. So maybe you write it this way, mgh, where h is a height above some reference point. So you might have the ground being h equals 0, and then some object up in the air. And h is like the height above or below some reference height of 0. But others may have always just used a change in height, and others might have used, instead of H, they might have used Y. So, but they're all basically the same formula. So when you apply work on an object and lift it up in the air, you're storing some energy in that system. You're increasing the energy of that system. You're doing work, and that stored energy is given by mg times that change in height. So a few important points. If you are a fan of MGH, and actually I like to do MGH when I'm doing conservation of energy problems, remember that this is still a change in energy, and it's a change in energy from some reference height h equals 0. Number 2, this formula only works if the change in height is small enough so that g doesn't change. Because I think at this point, when you guys investigated acceleration due to gravity in your grade 11 course, you talked about how it's around 9.8 meters per second squared on Earth. It doesn't really matter where you are on Earth. It's around 9.8 meters per second squared. But elevation and other factors can actually change g slightly. And if we're changing the height drastically, like say launching a rocket, then that change in g is actually significant. And we'll learn how to deal with that later. But if you're using MGH, we're using this in problems where the change in height is pretty small, so we can assume g stays constant. In the formula MGH or mg delta h, remember that this is a vertical displacement. It's a change in height, and so any horizontal motion during this change in height is irrelevant. So, for example, if I take my coffee mug and I lift it up, I've stored some gravitational potential energy in that. But if I lift it up and and finish at the same spot, even with that horizontal motion, so I lifted it up along a different path, it doesn't matter. If I lift it to the same height, I'm storing the same amount of gravitational potential energy in it. Delta H and delta EG are positive if the displacement is upwards. So if your displacement is upwards, you're storing energy in the system. You're increasing the gravitational potential energy. But if you're lowering something, you're removing energy. In delta EG, it is possible to be negative. And it's not weird or anything. It just means that energy is being removed. So let's do an example. So we have a pole vaulter clearing the bar at 4.2 meters above the ground, and then falls safely back to the mat. So we're going to say the change in their GPE from the bar to the mat is -2 times 10 to the 3 joules. And when he lays on the mat, he is now 0.7 meters above the ground. So we're going to find the pole vaulter's mass. I suppose I should have an apostrophe. I'm a math guy, not a, oh, I'm using yellow there. I'm a math guy. I'm not an English guy. So we can just deal with it. But yeah, there should be an apostrophe there. I'm not even going to bother. All right, so we've got lots of space for this problem. So I'm going to just draw a little visual. Sorry, somebody, looks like somebody came to the door at my house. So my dog's going berserk. The joys of teaching from home. I'm sure someday my kids will barge into the room and say hi. But so we have this pole vaulter, and I'm going to draw a very fancy pole vaulter going over the bar and then lands on the mat. So here's our problem. All right, now for me personally, if I was solving this problem, I'd try to make life easier for myself and choose some reference height to be 0 that simplifies the problem for me. But you have choice. And I think for this maybe initial example here, let's keep things easy. And let's say that h equals 0 is the ground. So that h1 is 4.2 meters and h2 is 0.7 meters. So it is possible to frame the problem in a different way. There would be nothing wrong with letting this height, h2, be 0 meters and using that as a reference height, in which case h1 would be 3.5 meters. And I actually like doing that a lot because something is 0, it makes the calculation simpler. But I think for this one, let's just use the ground as h equals 0, at least for the first one we do. And Yeah, here we go. So we have the change in gravitational potential energy is mg times the change in height. And we have everything we need here. Let's solve for m, because we have delta Eg, we have g, and we have the change in height. So delta Eg was given to us. It is negative 2,000. G is 9.8, and don't worry, we're not going to get a negative mass because the change in height will be negative, right? So if you can mentally just see it's negative 3.5 meters, that's good. Or if you just want to take H2, which is 0.7, subtract H1, which is 4.2. Remember, delta H is H2 minus H1. We will get a positive value for the mass. 2,000 divided by 9.8 divided by 3.5 negative. So pole vaulter about 58 kilograms. All right, so just a quick little review of gravitational potential energy, how to calculate it. Remember, it's always a change, whether you use mgh or mg delta h, it's always a change from some reference height of 0. All right, so now that we've reviewed work, kinetic energy, gravitational potential energy, we're going to do a couple examples of the law of conservation of energy. So you guys did learn this in your grade 11 course. For an isolated system, energy cannot be created or destroyed, only converted into other forms of energy. So a typical example of that would be like on a roller coaster. You start up really high, and as you go down and down and down, you gain speed. And then so you're at a very high speed when your gravitational potential energy is lower. But then when you go back up, you slow down because your kinetic energy is converted into gravitational potential energy. And that's traditionally the trade-off you guys investigate in grade 11. In this course, we're going to investigate elastic potential energy, electric potential energy, tie in a lot of different things. So we'll definitely expand on that. Some of you guys may have a, actually, let's just dive into the example and I'll show you how I set these up. So here we have a basketball player shooting a free throw, and we have the speed that the ball leaves the player's hand at and the height. And we're going to determine the speed of the basketball as it goes through the hoop, 3.505 meters above the floor. And so you can see in this diagram, we're using a reference height of the ground being 0, which often makes sense. So if you like y, that's good. If you like h equals 0, that's good too. I prefer h equals 0. But here's how I set these up. So I would say, I like saying that according to conservation of energy, energy before equals energy after. And then I'll usually write in my, from grade 11, really the two types of energy we focus on. So mgh1. You know what? I actually might just show one extra step here, just because it's our first example. So we'll have some initial gravitational potential energy, some initial kinetic energy, and afterwards we'll have some other gravitational potential energy and some other kinetic energy. So I like using 1 and 2. You can use I and F for initial and final. Really, it doesn't matter to me. And so we have mgh1 plus 1/2 mv1 squared equals mgh2 plus 1/2 mv2 squared. So one thing to note, we were not given the mass of the basketball, but in a lot of cases, it doesn't matter. Like in this one, because we have a factor of m in all the terms. This only works if you have a factor of m in all the terms. Now, in this question here, we have h1, we have v1, we have h2, so we can solve for it. I personally just like to solve for what I'm doing in a general sense. And to do that, I might clear the fractions. So I'm going to multiply everything by 2. I'll get 2gh2 plus v2 squared. And we're finding v2. So to get v2 by itself, I'm going to move over 2gh2. So I'm going to have my v1 squared. And I'll have 2GH1 minus 2GH2. So I might write that and just do a bit of factoring. So 2G, and I'll have H1 minus H2. That gives me V2 squared, and then I'll square root it. Hey, if you like to just plug in numbers and solve from there, then that is totally fine. Me, I like to do it this way. And so we have everything we need. Let's figure this out. So 7.2 squared plus 2 times 9.8. And then according to the reference height of 0 we've chosen, H1 is 2.21 meters, and H2 is 3.05 meters. And that's going to give us a negative for that part, which is okay, because we want to actually subtract off to get a smaller speed. Because if it's higher in the air, we've gained potential energy, but we've lost kinetic energy. So we should have a smaller value. Let's actually just do 2.21 minus 3.05 times 2 times 9.8 plus 7.2 squared, and then root it. So I've got that as it passes through the basket, it's traveling at about 5.9 meters per second. Yeah, and that's what I got earlier too. What I also just want to show you with this example here, if I rearrange this equation, and say I put the EG1 on the right, and so I'll have EG2 minus EG1, so just moving it over. And then if I move EK2 to the left, I get negative EK2 plus EK1. Well, this is just delta EG, right? And if you think about it, this is actually the flip of delta EK, because it's EK1 minus EK2. So it's negative delta EK. So what this shows is that in this scenario, a change in gravitational potential energy, so as the ball gets higher, leads to a decrease in the kinetic energy. So everything kind of fits together. And maybe in your grade 11 course, you use this equation as a starting point for a problem like this. I prefer to use something like I have set up in my question. But yeah, that was fun, a conservation of energy example. Let's do one involving thermal energy. So obviously we know that, what's a good example? Well, we just know that, no system keeps moving forever. Energy is lost due to friction and sound energy, and all kinds of things cause a system to lose energy. So energy is not perfectly conserved. Energy is conserved, but kinetic energy and gravitational energy won't be infinitely conserved. So maybe like a pendulum moving back and forth. As it moves back and forth, energy is converted from gravitational to kinetic and gravitational kinetic. But we all know that a pendulum, eventually due to friction and air resistance, will eventually slow down. And so sometimes we tie in those problems where we lose energy and where things aren't 100% efficient, we tie in thermal energy. So the equation for thermal energy is the following. So to get thermal energy, you take the force of kinetic friction times the distance something slides. So imagine something is sliding along a surface that has, and there is friction involved. It's going to lose some energy. Remember, guys, work is force times delta D, and you can remove, if work is negative, you can remove energy from the system, and that's what this gives you. This E thermal gives you the magnitude of energy lost due to friction. Fk is that kinetic friction force, and delta D is kind of obvious. It's the distance that you slide. So let's do an example where we tie that into our problem. So here we have a curling rock. And this curling rock slides in a straight line for 28.8 meters, experiencing friction. And eventually it's going to come to a stop. So we're going to find first how much energy is produced during the slide. So I think I'm going to squeeze everything here in this question. So According to my diagram, the curling rock is moving to the right, and then it slows down and stops. So what do I have acting on this? I have gravity, force of the ice on the rock, the normal force, and then friction is slowing it down. And I think hopefully at this point, it's pretty clear to us that with nothing else, the normal force here is going to equal mg, and that friction force is equal to mu times mg. Mu times Fn, so just be mu times mg here. So how much thermal energy is produced during this slide? So let's find it out. So it's the force of kinetic friction, or Fk or Ff. Maybe I'll just put Fk if you like using Fk for kinetic friction, times the distance traveled. Here we've already established Fk equals mu Fn, which in this case is mu mg. And we have all these things. 0.112, 18.2. I guess we can use G as 9.81 for sig digs, and goes 28.8 meters. So I didn't manage my space incredibly well there, but that'll work. So how much energy will we lose? Let's find that out. 9.81 times 28.8. So again, we're getting a positive answer here, because this is the magnitude of energy that we're losing. So I got about 576 joules of energy lost. Yep, it's what I got before. Let's set up conservation of energy with thermal energy. So how do we tie in? Because in this case, obviously the energy before does not quite equal the energy after. So how do we modify this equation to deal with that? Well, the energy before does equal the energy after if you add in that energy lost due to friction. And so if you want to just go right to this, you can. So the energy before, gravitational potential energy, kinetic energy, mgh2, mv2 squared plus the thermal energy. And let's just actually talk about some things we can remove from the equation here. If we choose h equals 0 to be the ice, which makes a lot of sense, and if you don't do that, I would question your sanity there. But yeah, h equals 0, which means we don't have any gravitational potential energy with respect to the Earth's the ice surface. So that's 0, that's 0. We know that Vf is 0 when it slows down. The rock comes to a stop. That's 0 as well. And so we have that 1/2 mv1 squared equals E thermal. So all that initial kinetic energy got converted to thermal energy. And we calculated that, so we can actually find V1. So V1, so we'd multiply up to 2. We would divide by the m, and then we would square root. And let's squeeze this in and finish it off. 2 times 576 divided by the mass, 28.8. And root, about 6.32 meters per second. Did I do that right? 28.8? No, 28.8 is the distance. Okay, I didn't get what I got earlier, so I just double checked that. Yeah, because that's 18.2. So I got 7.96 before, but I'm going to double check that because I don't trust myself anymore. About 18.2, shift root. Yeah, 7.96 meters per second is what it left its hand with. All right, so we did a lot in this review one. And you know, if you bailed earlier or you fast forwarded ahead because you're kind of comfortable with all this stuff, that's great. But we are going to be expected to use all this knowledge of work and work energy theorem. We want to be pros with gravitational energy and kinetic energy and thermal energy and applying conservation of energy. So I have some practice for that. But now that we've reviewed work and energy concepts, we're now going to learn about another form of potential energy. And this is the energy stored when you compress or stretch a spring or an elastic band or something like that. It's called elastic potential energy. So it's pretty interesting, pretty cool. We'll be talking about that next lesson. For now, hope you guys stay well. Hope you guys have a great day, and we'll see you soon.